Hey, it's Mr. K doing another video for AP Physics C Mechanics. We are still talking about motion, kinematics, and it's going to be still a bit of algebra. We're going to try to bring in some graphing, but a little bit of a recap so far. We've talked about displacement, we talked about distance. Remember, displacement is the difference between one position and another. It's just straight up, what's that difference? Distance would be the inclusion of all the motion in between. So imagine if you were a sprinter, a track runner. You're going around the track, around once, around twice, around 3 times. Your displacement would essentially be nothing if you ended up where you started. But if you were that sprinter, you would argue, I definitely went somewhere, and so that would be your distance. It would be however many times you went around that track. That, 400 meters around the track. So if you had gone 3 times around, you'd go 1,200 meters, almost a mile. And so you have those two basic things. We talked about velocity and speed. Velocity would be how far you went over a time taken, and that would be in a certain direction, so that would be velocity. So it's a ratio of how far over how long. Displacement over time is really what it is. And then there's this thing called speed, which is going to be very much like velocity, except that we are not going to care about direction, and it's going to be based off of distance instead of displacement. And so those two things would define how fast you're going. And then we also talked about acceleration, which is a change in velocity over time. And so right now we have a couple of these equations. Here they are. We just said another one. Acceleration is a change in velocity over a change in time. Average velocity is going to be very important to talk about, which is going to be the initial velocity and the final velocity divided by 2, assuming that we're under a constant acceleration, of course. And yeah, we're going to start here. There's actually one more kinematic equation that we need to introduce, and it's going to be this one that is based off of energy, and we're going to bring that topic up later. But really, you can get it by combining these two equations. So if we were to combine these two equations, one thing that we would really want to do is we want another equation that does not rely on time. And so in order for me to get rid of time, I'm going to solve this first equation for time, final velocity minus the initial velocity, move that sucker over, and we're going to divide that by the acceleration, and that's going to equal a change in time. So it's just that first equation solved algebraically for time. We're going to take that time and we're going to plug it in to these spots here, and we're going to see what we get. So all we're doing is we are formulating, we're deriving another equation that does not rely on time itself. And so I'm going to probably speed through this with the video editing, but right now, let's just go ahead and hit it. And let's see what we have here. We got some minuses and some pluses there, so we can get rid of that. We can get rid of this. We've got VF and two V naughts and one V naught, so let's get rid of this one and get rid of this thing. And let's clean this thing up. We've got the following. 2a acceleration change of position is equal to negative v initial squared plus final velocity squared. And let's make this even nicer. Move that initial velocity over. I don't like that negative there. So we've got the initial velocity squared plus 2a change of position is equal to your final velocity squared. So this is another kinematic equation. In my class, we usually refer to that as the second kinematic equation. So there's going to be a total of 3. First one is derived based off of acceleration. Second one was derived from the graph, as well as looking at what it is to have average velocity for a time. I think that was last video. And then the second equation, first, third, second equation here is what we just did. This one is I think it's called Torricelli's equation, and it's really based off energy. Really good equation. You'll get mad at it later as to how simple it makes problems seem, but that's energy for you. So 3 equations to work with. For you, I would recommend writing these down. Final velocity is equal to initial velocity plus acceleration for a time. Remember, all these are assuming constant acceleration. This equation that we just derived, and then of course the change of position is equal to the initial velocity times time plus 1/2 the acceleration times time squared. So these three equations here are going to help you out whenever you're doing kinematics. Kinematics is really just math. Straight up, it's just algebra, knowing how to plug things in. And for right now, let's just go ahead and do a problem, and we will end this video with that. So going back, let's say we have a problem. We're gonna throw something up. We're gonna take this, we're gonna throw it up into the air, and we're gonna figure out how long it takes for it to get back to our hand based on an initial velocity, I guess, or we can say it's in the air for X amount of seconds, or like T amount of seconds, really. Let's just draw it out at the moment. I don't know what's going on with this pen. This pen is a finicky pen. So we'll stick with red. So let's say we have a person. Here they are, and they are throwing a ball. And ooh, let's make them on a cliff, even better. And they are throwing this ball, and they're going to throw it upwards. So we're going to give it some velocity upwards. And with that, we're going to say that it has an initial velocity of 20 meters per second. And that's upwards. Now, as the ball goes upwards, we know that it's going to be pulled on by gravity, the force of gravity. We're not the forces yet, but we can still talk about it. And that force of gravity is going to change the velocity of the ball, and it's going to change it by 10 meters per second every second in the downward direction. So we'll say that the acceleration of the ball is 10 meters per second every single second, so meters per second squared, and that's in the downwards direction. The initial velocity is in the upwards direction, and the way that we denote the other way is by putting a negative. So that's where you're using negatives. We're working on a number line here, and we're just going the other way. So we start going up 20 meters per second. Gravity is changing our velocity by 10 meters per second every second, and we're going to get to some height up here. I don't know where, but it's going to turn around and it's going to come back down. And so we can talk about a lot of things with this. We can even draw out the graphs, but right now I just want to talk to you about it. So let's just talk our way through the problem, and then, for the more mathematically minded, we'll take a look at the equations. And so let's just start here. How high does it go? Well, it gets up here. We know that the velocity at the top, if we threw it straight up, the velocity at the top would be 0 as it's turning around, just for that one instance. And so for it to get to a velocity of 0 meters per second at the top, assuming we threw it straight up, not to the side at all, we're not doing projectile motion yet, how long would that take? That would take, well, knowing acceleration's definition, that's going to take 2 seconds. So the time to get to the top of the path is going to be 2 seconds. And this is just, again, talking the problem through. Well, if we know we go from 20 meters per second upwards to 0 meters per second, what's the average? Well, the average between 0 and 20, assuming constant change, is going to be 10. So my average velocity on the way up is 10 meters per second. Okay, again, we're trying to keep the math out of it. I'm trying to keep this as a physics class right now. We're going to apply the math in just a second to show that we have the exact same answers. If we know we are at an average velocity of 10 meters per second, we're moving for 2 seconds, how high do we go? Well, average velocity is 10, time is 2, we went a total of 20 meters. Okay, went 20 meters on the way up there. That's how high we go. The thing's going to fall back down. If we fall back down, we got to fall down 20 meters. Well, we're accelerating at the same rate as we were before, right? So how long would it take to get back down? It's going to take 2 seconds. So to get from here to there, all the way back down to our person level again, that's going to take a total of 4 seconds. Okay, and we can keep on going with this. But let's just go ahead and prove all these things. By the time it gets back down to us, let's call this T cliff again. Back to the cliff. That's going to be a total of 4 seconds. The velocity that we are back at with T cliff is going to be 20 meters per second downwards. All right, and all this stuff that we just talk through it. A lot of times, whenever the numbers are nice, you can just talk through it. If the numbers aren't nice, then use the equations, and then you can also back it up with graphing. So, right now, let's just apply some of these equations that we have. Well, if we wanted to figure out the time to get to the top here, we could apply, looking for time, we can use one of these two. Well, we didn't know how high we were. We didn't know the displacement in the first case from here to there. So we would have to use that very first equation that we deal with. Final velocity is nothing. Initial velocity was 20 meters per second. My acceleration was -10, and they would take some time to do that. All right. Well, what makes this equation true? That's if time is 2 seconds, right? So the time to get up there is 2 seconds, and this confirms exactly how we talked about it earlier. Again, I want this to be more of a conversation as to how to solve these problems instead of just straight up math. So, what else? How high did it go? Well, if we want to find out how high it went, let me use this equation here to figure out how high it went. So that's going to be a change of y, going up instead of left, right. So let's just use y. My initial velocity was 20 meters per second. I know that I'm going to be moving for 2 seconds now to get up there. That's my initial velocity times my time. Plus 1/2, what's my acceleration? Well, it's -10. Make sure that negative's in there. And then you have time again, 2 seconds, and that's going to be squared. And so this is where a lot of people will get lost in the math. A lot of students will focus too heavily on the math. And remember, we've already solved this problem without even using the math, but just by using the understanding of physics. So here, let's just go ahead and do it. 20 times 2, that's going to be 40. -10, we've got -10, we've got half of that, that's going to be 5, -5 there. And then the 2 squared, that's going to be 4. So that's 5 times 4, that's -20. And so we have 40 minus 20. What is that? It's going to be 20 again. So 20 meters in order to get up there. We already knew that. It's up here, just by talking it through. But the math will help you out, especially if the numbers aren't nice. Okay. What about whenever it comes back down to, we come down and catch it again? What happens at that point? Well, if we consider displacement back to the beginning again, the displacement is 0, right? So let's take a look over here. If we have a displacement that is 0, then this is 0, or this is 0, right? And so if anything is multiplied by 0, you just cancel out the whole thing. So what does this say? This says that the initial velocity squared and the final velocity squared, if your displacement is 0, is the same thing. Okay? But there's one important difference. Our initial velocity was 20. Our final velocity will be 20 that way, right? Because we're coming back down. And so that's where you might get messed up. You just might forget to put that negative there because the math would tell you, hey, it's a squared number. It must be the same value. 20 squared is equal to 20 squared. Well, -20 squared is also equal to 20 squared. So here we find out that the final velocity is 20 downwards, but you need to put the negative. That's going to be on you. Okay? Over here, you could say our initial velocity is 20 meters per second. And now we can solve for, let's say, time. How long would it take to get back to the same position? And so we have 0 is equal to 20, time is unknown, plus 1/2, a is -10, and then we have this time again that is unknown. Well, let's go ahead and move this over there. We're going to change the -10 to -5 because it's divided by 2. And so let's move this whole term over. So we have 5t squared is equal to 20t, delta t. And then you think, well, crap, Mr. K, how do you solve that? Man. Well, you're forgetting we can just divide both sides by t. So, divide both sides by t, just 1t. And we get 5, change in time is equal to 20. 20 what? 20 meters per second. So, our units working out. 5 meters per second. Actually, no, that's fine. So 5 meters per second squared is going to be multiplied by time, and then that's going to equal 20 meters per second. What times 5 is equal to 20? That's going to be 4. So, we've done this problem with kinematics, the kinematic equations, and we've done it with just thought, logic, understanding of definitions. There are problems that you're going to have to use the equations. On the multiple choice problems, though, for Physics C, Physics 1, Physics, all of them, you really should be able to talk your way through it. And I want this to be more of a conversation for you whenever you're trying to solve a problem, and then later on, whenever you have to, you make it into math. All right, we'll stop it here.